Ah! You shouldn't be sneaking up on people like that. You almost scared me half to death. But listen, now that you're here, might as well do some math. What's up? So, the past couple classes, we've taken a brief reprieve from our abstract symbols and we've dipped our toes into the cool, refreshing waters of word problem land. But just like you were a couple seconds ago to me, word problems can sometimes feel a little scary. So let's go back to where we feel safe and sound. We'll loop back around to solving some equations for a bit. Pause for applause, and we're back. But this time, the equations that we're going to be interested in solving might get a little funky. So the title of our lesson today, let's talk about some funky equations, our 6th class of Unit 1. Now this equation should not feel particularly funky. It should in fact resemble stuff that you've done before. Again, remember, it can never hurt. What's my goal here? What am I trying to do with this equation? Not what am I trying to do to it, like what am I trying to make it look like, but like what is the goal? What am I trying to do with this equation? I want to make it something. What do I want to make it? Go. 5, 4, 3, 2, 3, 2, 3, 1, 3, and stop. I want to make this equation hate me. No, I want to make this equation true, which of course means I want to get the variable by itself. I want to find the value that when I substitute back in makes both sides of my equation equal to each other. Cool. So let's do it. Give yourself a 2-minute timer. Solve for x. What value here is going to make this equation true? Alrighty, so I've got x plus 3 parentheses x plus 4 equals 7 minus parentheses 4 plus 2x. That was a lot of parentheses. Well, maybe I want to get rid of some of them. A good opening move, let's simplify, right? So I want to put these x's together. I can't do that until those dirty, stinky, smelly parentheses go away. Well, one way that I can do that is to use the distributive property. So here I've got a plus 3 on the outside. On the second pair, it looks like the 7 might be there, but don't fall into the trap. It's not the 7, but the negative sign that's immediately outside of those parentheses. Cool. So I've got x plus 3, parentheses x plus 4. Well, the x stays, give my 3 to both the x and the 4. Then I've got 7. Distribute my minus signs, so then I get negative 4 minus 2x. Cool. And from here, I'm in familiar territory. I've got like terms I can combine on the left, like terms I can combine on the right. X plus 3x is 4x plus 12. On the right, 7 minus 4 is 3 minus 2x. I again want to get all of my x's over to one side, all of my constants over to the other. So let's say I want to move all of the x's over to the left. So I will add 2x to both sides. On the right side, negative 2x and plus 2x, these friends undo each other. 4x plus 2x becomes 6x plus 12 equals 3. Now I want to isolate x. Well, let's subtract 12 from both sides, our reverse order of operations. Plus 12 minus 12, these guys go away. 6x equals negative 9. Last thing between me and freedom, let's divide both sides by 6. On the left, 6 over 6, these undo each other. X equals negative 9 over 6, and I'm done. Except I'm not, because 9 over 6 is not fully simplified. That's negative 3 over 2. And now I'm actually done. Haha, did I scare you like you scared me in the beginning? Let's call that some retribution. Cool. Let's do 2 more. So you know the drill. I've got these 2 equations. Again, my goal is to make this equation true. Let's find the value of the variable so that when I substitute it back in, I will get a true mathematical sentence. Go ahead. What do you mean? What do you mean your eyebrows are raised? What do you mean you're confused? What do you mean this doesn't make sense? Don't be silly. You're going to feel so silly when we solve this together. So 7 parentheses 3 minus w. Obviously, right? I want to get rid of that parentheses. Let's do it with the distributive property. So I'll take 21 minus 7w equals, well, 7 times 3 is 21. 7 times negative w is negative 7w. Let's say I want to move all of my variables over to the left. So then I'll add 7w on the right. What I do to one side, I do to the other. We'll add 7w here. On the right, negative 7w and positive 7w, those undo each other. And on the left, that leaves me with 21, negative 7w plus 7w. Well, but negative 7w plus 7w? Negative 7 plus 7, well, isn't that 0? So I get 21 equals 21? Well, that doesn't totally make sense. Maybe if I subtract 21 from both sides, then something will like help me out here. Well, 21 minus 21, that's 0. And then I've got on the right I also have 21 minus 21, but 21 minus 21, that's also 0. So 0 equals 0? Huh. Well, hold up. So this one is a little funky. But why? You tell me, what makes this equation different from the equations that we've seen before? Why is this one funky? Why is it wonky? Why is it weird? Why is it different? Okay, well, maybe you've got an idea percolating. Let's puzzle through this a little bit. Maybe if I'm trying to solve this equation, it can help me to remember what it is that I'm trying to accomplish. Well, if I think back to the idea that we articulated back at the beginning of class, well, if I'm trying to solve an equation, I can think in terms of my goal. I want to make this equation something. Particularly here, I want this equation to be what? Well, I want it to be true. So my goal is to make the equation, I'm going to abbreviate EQ, true. Well, if I want to make the equation true, that means, as we've said earlier, that my goal is to find a value so that when I plug it back into the equation using substitution, it makes both sides equal. Well, the thing that's funky about this equation is, well, here, both sides are equal. 21 equals 21, that's equal. 0 equals 0, that's equal. 21 minus 7w equals 21 minus 7w. Both sides are already equal. So I've already accomplished my goal. Both sides of the equation, not only have I made them equal, but they are always going to be equal no matter what I do. So the sides of this equation are always going to be equal. And if the sides are always equal, that means the equation is always solved, which means that the equation is always true. And if the equation is always true, that means no matter what I plug in, right, anything will work. So what does that mean for my solution set? What does that mean for the answers to this question? What value or values of this variable will make the equation true? Take 30 seconds. What do you think? Talk to yourself, talk to a partner, talk to somebody, talk to the wall. What do you think this means about the solutions to this equation? Go. Well, if the equation is always true, then that means that everything works. There is nothing that I could put in that could make this equation not be true. So if everything works, that means that I no longer have just one answer to this question. In fact, right, let me just check to make sure, like off to the side, let's say I check. Say that w is 1. Well, then I would have 21 minus 7 times 1, which is 7. Is that equal to 21 minus 7? Yeah. What if I did 21 minus, maybe w is 0. So then that would be 21 minus 0. Is that equal to 21 minus 0? Yeah, I could keep going. And I hope that you'll see that no matter what I put in for w, both sides will still always be the same. So I have not one number that makes this equation true, but any number that makes this equation true. There is not just one solution, but infinite solutions. So there are infinitely many answers to this question. I could take any value, a decimal, a fraction, a negative number, 0. All of those would make this equation true. A shorthand that you'll sometimes see for infinite solutions, some people like to write infinite solutions like this. This symbol, it's kind of like a bold R. It does not mean IR, but it looks kind of like it. It's a bold R. Like if you've ever seen like that bold kind of up here paragraph symbol, it looks kind of like that. So this bold R does not mean infinite solutions. It means the set of all real numbers. So that's a shorthand for saying anything, right? I could plug anything in and it would work. So this equation has infinite solutions. Take a look at this second one here. Think, how is this different from the last one? And what might that mean for its solutions? If you haven't already, take some time and solve this. If you did already solve this and you were stuck, try and unstick yourself by comparing it to the problem above. How is this different and what does that mean for its solutions? Go ahead. And come back. So in this case, I have 3 parentheses 5x plus 2. Again, same strategy. Maybe I try to get rid of my parentheses first by distributing. Well, this becomes 15x plus 6 equals 15x minus 1. And then again, I want to get all of my x's over to one side. Let's subtract 15x from both sides. You may already notice a pattern here that's forming between these two. Well, 15x minus 15x, that cancels out. 15x minus 15x on the other side, that cancels out. And I'm left with 6 equals negative 1. So again, think back to the goal. When I'm solving an equation, I'm trying to make it true. Well, look at this. 6 equals negative 1. Is this a true mathematical statement? Well, above 0 equals 0, yeah, that works. 21 equals 21, yeah, that works. By the reflexive property, anything is equal to itself. But can 6 ever equal negative 1? No. So what do you think that means for the solutions to this equation? Come up with some ideas as I write some stuff. So the idea here is that unlike above, where my sides were always equal, here, the sides of this equation, they will never be equal to each other. I can never make 6 equal negative 1. So if I can never make my sides equal to each other, that means that I can never make the equation true. So if the equation is never true, it is fundamentally false, nothing that I plug in can ever make this equation true. So is there a solution to this equation? Well, it turns out no. The answer to this question, there are no solutions to this problem. And just like the set of all real numbers is a shorthand for infinite solutions, no solutions is represented also by a set. The set that we use here, it looks like a 0 with a slash through it. It's called the empty set. So the empty set, that 0 with a slash through it, it is the set that contains nothing. Okay, so you've got your idea here. Some equations can have one solution, and on rare cases, there can be infinitely many solutions, or in fact, no solutions. Everything and nothing could make the equation true. Okay, let's take a little bit of time and do some practice. So I'll scroll down and give you another. I've got 2/3 parentheses 3f plus 27 minus 16 equals 2 parentheses f plus 1. Let's solve this equation and see, is it in fact one of our funky cases? Give yourself 2 minutes. Go ahead. And come back. I missed you. Okay, So the first move that I can make, 2/3. Let's take that guy and distribute it. So I've got 2/3 times 3. Well, 2/3 times 3 over 1. I have 3 and 3. These guys cancel. I'm just left with 2. So this is 2f. And then 2/3 of 27. Similar process here. That should be 18, right? So 27 divided by 3 is 9 times 2 gives us 18 minus 16. And then on the right, I have my 2. I'll distribute it. That becomes 2f plus 2. Again here, like terms on the left, I can combine. 2f plus 2 equals 2f plus 2. And here, you're functionally done if you realize what case we're in. But just to make it really obvious, let me also get all of my variables over to one side. When I try to do that, you'll notice 2f minus 2f. These cancel out on both sides, and I'm left with 2 equals 2. Is 2 equals 2 true or false? Go. 2 equals 2 is trivially true. So in this case, both sides of my equation are always going to be equal. What does that tell me about my equation? Well, it must have infinitely many solutions. So I'll use my fancy symbol, all real numbers here. This has infinite solutions. Cool. Let's do a couple more. So I'm going to scroll down. Let's just do these four. If you want, I'll scroll down and give you the last two. But we'll stop over here. If you want to do a little extra practice in between now and class, be my guest, do the last two. But let's start. 8 plus 9p equals 9p minus 7. You can read, I don't have to read them for you. Tackle those first four. If you want to tackle those last two, be my guest. We can talk about them next time we see each other. Go ahead. Okay. 8 plus 9p equals 9p minus 7. Well, again, my goal is to get all of my variables over to one side. I'll subtract 9p from both sides. When I do so, it turns out they undo each other on both the left and the right. I find 8 equals negative 7. Is 8 equal to negative 7? No. Will 8 ever be equal to negative 7? No. Can anything make 8 equal to negative 7? No. So this equation has how many solutions? Well, nothing works. It has no solutions. Cool. 5 plus 30n equals negative 4 parentheses 3 plus n. Same idea. Use some distributive property. Here 5 plus 30n. Negative 4 times 3 is negative 12. Negative 4 plus n is minus 4n. And from here, I'm just going to combine some like terms by using some inverse operations. So here, let's add 4n to both sides. I usually like it when the variable has a positive coefficient, but it doesn't really matter. On the right side, they undo each other. On the left, I get 5 plus 34n equals negative 12. Let's subtract 5 from both sides. When I do so, they undo each other on the left. 34n is going to equal negative 17. We'll divide both sides by 34. And when we do that, 34 over 34, these guys go away. And n equals, well, 17 goes into 34 how many times? Twice. So negative 17 over 34, that should reduce to negative 1 over 2. Cool. So this one has how many solutions? 5, 4, 3, 2, 1. It has exactly one solution. So always either one solution, no solutions, or infinitely many. Let's see about this guy. 12v equals negative 3 parentheses 1 minus 4v. I'll distribute my negative 3. I get 12v equals negative 3. Negative times negative becomes positive 12v. Subtract my 12v from both sides. Subtract my 12v from both sides. On the left, they cancel. On the right, they cancel. We find that 0 is equal to negative 3. What do we think? Yes, no, maybe? No, absolutely not. 0 cannot equal negative 3. This has no solutions. And finally, negative 2, parentheses 4a plus 1, I'll distribute. Negative 2 times 4a becomes negative 8a. Negative 2 times 1 becomes negative 2 equals negative 8a minus 2. And then from here, again, we should feel pretty good. We don't even need to go any further, but to make it really obvious, let's add 8a to both sides. When I do that on the left, they cancel. When I do that on the right, they cancel. We find that negative 2 equals negative 2. This is, of course, an incorrect statement. No, I'm kidding, it's true. So if this is true, my statement is always true. Nothing can make this not true. This equation is fundamentally true. It has infinitely many solutions.